detail this morning, so I'm going to go pretty light on this. But I do want to emphasize a couple key points about how data gets into model, where it might be drawn from, and the different ways that we might take that into account with statistical versus dynamic models. So in this context, we have, if we think about models and their interface with data, there's broadly data that's introduced into the model that we tell the model to assume, either direct estimates provided from parameters, and I'll talk a little bit about some of the places those come from, and then through a process known as calibration, we're actually matching data output by the model with empirical data. Empirical data that by itself doesn't tell us about any one parameter in isolation, but rather collectively constrains our interpretation of what plausible values of the model parameters would be, because you will find often that the model just can't match this empirical data without assuming certain ranges of values for parameters. There are also cases, of course, where, well, there's a huge amount of data that's produced by these models. Generally, the models that we build have many output variables. In fact, what you call an output variable is a matter of choice, typically. If it's an endogenous variable, if it's calculated by the model, it's a candidate for being considered an output variable. And by being an output variable, it can still be endogenously affecting other factors. So, output variables commonly contribute to governing processes. They commonly shape the evolution of a model. In a system dynamics model, for example, we'll have these parameters. We saw them yesterday as denoted by those sort of pie slices associated with parameters. This is another system dynamics modeling framework where they're not as visually distinctive, but we might have something like, the likelihood a given obese person will become diabetic on a per year basis. So this would be a hazard, per year hazard. Probability per year someone becomes diabetic, for example, given that they're obese. Or there might be a mortality rate that applies for someone who's non-obese within the general population that would lead to mortality of individuals. And depending on the model, whether it's a system dynamics model or an agent-based model, this could be further delineated by age of the person, their sex, some aspects of their income, etc. So often we will be taking data items and put them in as assumptions. These are empirical data drawn perhaps from surveillance studies, from controlled trials, from outbreaks, from intervention outcome studies. In some cases, they're drawn from meta-analyses. And in some occasions, we will, without embarrassment, but with a very clear documentation of the fact, consider judgments that are based on direct observation of people within the system, but which lack clear empirically grounded, rigorous studies by which they're estimated. So these are commonly called expert judgment, and you will find those for a large number of models as a source of evidence. It's a source of evidence that needs to be scrutinized in terms of sensitivity analysis and in terms of performing tests of the model to make sure that it doesn't that uncertainty there doesn't disproportionately affect the impacts of interventions. So Matt had talked about sensitivity analysis before, and I think to illustrate this, I would suggest you might consider using the NetLogo interface that he had created. Alternatively, within any logic, you will find a quite nice demonstration. If you go to the example models area, there's a model here called SIR agent-based calibration that also provides you with an interface for sensitivity analysis. And if you were to open that, what you would find is that there's this last experiment here, which if you run it, will examine the impact, for example, of running your model 100 different times with stochastics only caused by the model, sort of summarizing its variability in a 2D histogram across many runs of the model. Alternatively, you can also, with that same experiment, elect to change parameter values within some ranges. And the key would be to go to this area and say varied in range. And you can say, I wish to vary, for example, this parameter from a value of 0 to 10 on a step 1, or you could vary multiple of them at once, and you could use that to sort of understand how the output of this model might change for different values of the parameter. And unfortunately, the screen is not sufficient to bring it out, but there's some variability caused here as you change the assumptions about that parameter that I can see on my screen, but doesn't come out well there. So this is a process of systematically varying parameters, either in a fixed way or with a Monte Carlo draws from probability distributions to understand how uncertainty in that parameter might affect either model outputs, key model results, or more deeply might affect the level of benefit conferred by different intervention options. Because often what we care about most is whether our intervention evaluations are significantly affected by parameter values. And so you may wish to run certain intervention evaluations with alternative values of these parameters and see if they, for example, might reverse the level of desirability comparatively between intervention A and intervention B. Maybe before it seemed intervention A was more favorable to B in terms of health burden or in terms of cost effectiveness, but the reverse could also be true. So often we don't have reliable information on certain parameters. Instead, we have information more on the emergent patterns we see from the world, in which case we'll engage in a process called calibration. We'll try to match the model against the data in a quantitative fashion. And again, the same AnyLogic model that we used here has this calibration experiment that you may wish to run. This is this SIR agent-based calibration that I got through example models by scrolling down on the right. And if you run this, you'll get the basic idea behind calibration pretty quickly. So here, if we run it, you will find some historic data shown. There's an agent-based model behind it. If you were to go explore this particular agent-based model, you'll find, for example, a person's state over time is illustrated with a state chart. And you could run the calibration here, and it's trying to match the model results for different values of parameters as closely as possible with this empirical data. And you'll find over time it's finding matches that are closer and closer in character while still running for a given set of parameters, a given assumption about the parameters. It runs the model several times to make sure it's not just a fluke of a single run. In other words, a single realization. It'll run many, what it calls replications, or what would come be called realizations of the model. So here we're running the model many, many times, and for each time, or we're running it for different values of parameters in a clever sort of way using what's called genetic algorithms. And for a given assumption about those parameters, we'll run the model several times with those parameters to see how well it matches the historic data. And if it matches very well, we'll remember that set of parameter values, and ultimately it will be reporting the best assumption about parameter values that yielded the closest match to this point. In general, we perform this for matching not just one particular time series, but we may match several lines of data. They could be time series, they could be specific data points, or they could be qualitative features of the situation. We know, for example, the rate in men is higher than the rate in women, and we discard runs or parameter assumptions where that's not the case. So here we're running the model again and again and again, trying to find parameter values that yield the best match to what may be very noisy values. This is a result from one of our models, a system dynamics model that involved end-stage renal disease, type 2 diabetes, etc., with an agent-based model, the model results, the outputs from the model that are being matched to this empirical data, those output results are themselves stochastic. So there's going to be some more variability in these red and green lines that are shown there. Okay. I think I'm going to skip over some of this material so we can finish up on time. But what I will say is that when you're dealing with models, it's very worth reflecting on the fact that there's a central motivation for the use of dynamic models to examine counterfactual situations which have not yet been observed. And we're seeking to use the model to understand what would happen if we institute this policy that's never been instituted before? Or if we were to put in place this new screening mechanism, how might that affect the reported cases of a given illness? And it's worth noting that putting in place this counterfactual is likely to change the data generating process, the process that gives rise to empirical data. And this is one of the reasons we can't pursue this so readily with statistical models. Statistical models are contingent on the associations which have been observed, but if we're changing the processes, the way in which those processes operate that give rise to those associations, we may find those associations change quite a bit under an alternative policy regime or an alternative situation down the line just due to sort of natural demographic shifts in the population. So this is one of the big motivations we use simulation models, is to ask about counterfactual situations. But to develop confidence in a simulation, we typically run that simulation for a period of time with historic data to develop confidence that it accounts for known quantities. So we develop confidence that the simulation is capturing processes as they are before then turning our lens to counterfactual situations. It's important to distinguish those two in our mind. And one of the most powerful best practices you can use here is something that's called cross-validation. And in cross-validation, one sets aside a certain amount of data that would otherwise be used to build the model, to directly inform the model, but you set it aside in escrow, as it were, for recourse later. You build the model on a somewhat smaller set of data. How much you do of this may depend on your data availability. But if you build the model then on the other data, you can see to what degree the model that's so built on this other set of data predicts the model on this data that was set aside. So in other words, you're testing the predictive validity of the model by reserving some data to check the model, not to build it. This is called cross-validation. It's a very good practice if you can undertake it, and it's one that's increasingly common in many areas. It is considered central to the practice of other areas of modeling that are more statistical in nature, such as in machine learning. But it is a best practice within the dynamic modeling landscape. So I've talked briefly about calibration. Be aware that with calibration, it's an expensive operation, particularly for agent-based models that are stochastic. You have to run a model many times for a given set of parameters often. And it may be that the one result you get for the parameter values is not terribly privileged. There may be many consistent assumptions about parameters that would give rise to the empirical data. And calibration can help you spot ambiguities like that if it's used artfully. Calibration is also most emphatically a learning process, because often what you will find is that it doesn't add up. No matter what you use sort of the assumptions about these parameter values, the model will not account for this empirical data. I mentioned that a few days ago, and it's not a failure of modeling. It shouldn't be thought of as a giant setback. It should be thought of as a giant leap forward for learning, because you will learn something about either the data or the model that will help you move forward in a more informed, judicious, and robust fashion. So just be aware, though, that calibration is not a magic process. I've spent a huge amount of my professional time engaging in calibration efforts, and there's a science and an art to effective calibration. Suffice it to say that the more data you have to inform the constraints, to constrain the calibration, the better. The more parameters that you're trying to calibrate, the worse, or the harder it will be to get a unique match, certainly. You have to be very cautious about wading into a calibration with dozens of parameters, because you may not find anything that's unique or even an adequate accounting, because the search space, the space of all possible combinations of parameters, is just too large. It's too bushy. It exhibits the curse of dimensionality. We're going with one parameter, you're searching a line. With two parameters, you're searching like a piece of paper, a two-dimensional space. With three parameters, you're searching a box. With four parameters, well, I'll leave it to your imagination, but you're searching ever larger sort of volumes. Time is running short, but in calibration, you need to specify what you're trying to match, what parameters you want to vary, and you want to specify something about the characteristics of the desired algorithm to verify them, by which you're trying to improve your estimates to get better and better. But in some cases, you also specify constraints for what legitimate parameter values are, or constraints in what particular model outcomes are. So you're trying to search a space for values of different parameters. A quite involved process computationally, but one which can be done often overnight to an acceptable level for smaller models. So, well, what if you don't have the data? Well, what if you do have the data? Is sometimes what I ask people. Behavior of dynamic models depends heavily on understanding theory as well as data, and we have to understand that even the most detailed models have a lot that they draw from understanding that's other than data itself. It's understanding about the system, the etiology, the underlying processes, and how those processes work. It may be the natural history of infection. It may be aspects of how two comorbidities interact. But there's a lot of understanding that's built into these models besides data. And as Ross said, it is fraught with problems to look to the models to predict outcomes on an ongoing basis. It's a fool's errand to ask the model to provide an exact anticipation of what's likely to play out in the next 3 months with an outbreak, for example. A model can give you a sense of the trends, but if you think about real-world processes, as Ross noted, and I think as Matt noted, our observations of the world are observations about a single realization of a process. And without getting into philosophy or deep physics about multiple worlds hypotheses, suffice it to say that there's a lot of different ways that the world could go that are quite likely. And even the best of models, the most finest of models built with the best funded resources and the best evidence brought to the table, will inevitably be unable to capture precisely aspects of the world's operations. Stochastics that will be left out of the model involving the vagaries of weather and of economic dislocation and shifts, oil prices, and many factors that may ultimately end up impacting your model. There will be factors omitted from the model because all models are simplifications, and there will be approximations in models which are often cruder in an aggregate model, but even in the most refined individual-based model, ultimately are approximations. We characterize people's decision-making behaviors in ways that probably 100 years from now, 200 years from now, will be considered sort of shockingly naive. And for all these reasons, models will inevitably diverge. And more than that, though, folks, that shouldn't be a cause for lamentation and breastbeating. Interventions change things. We are often looking into the future where we have bent the curve. We have changed the processes that are operating. We are changing the data-generating processes upon which we have gathered data thus far. And we will be changing things in many ways we can't yet anticipate. there's not the empirical data or understanding of processes to understand fully how our interventions may affect vagaries of human behavior. And often, when we're looking forward into a counterfactual future where we are seeing a very different reality playing out, we will have to recognize that even the best of models will inevitably diverge to some degree, and we should not view it as a failure of a modeling process if our model is off in certain respects. So to what degree, what if you don't have data available to you? What if you're operating in an area where there's profoundly important human factors involved, that a lot is known about them at a basic qualitative level, but there's not the empirical evidence because they're slippery to measure, or we're not quite sure how to reliably measure them in non-invasive ways? Well, we can still get strong evidence captured in the form of model structure. Our understanding of the basic progression of factors, and in some cases can be strong, and we can still gain deep insight as to how process assumptions affect possible outcomes, and how interventions might at a broad level affect what's likely to play out. I think Ross did this a good justice earlier, but these sorts of models can still greatly inform our sense of where to start in terms of prioritizing data collection in a way that's very, very important. I think I'll leave the comments out on stylized models, but just remember, from my perspective at least, models serve as these thinking tools, these thinking prostheses, and even when we lack data, that's some of the times that models can be most valuable in building theory, most valuable in pointing us where to start the process of data collection, and most value in terms of giving insights into a world where the empirical evidence may be sparse. So those are some comments on models and data. I did want to make a few comments on the issues of statistical models and dynamic models. Unfortunately, this is sometimes characterized as a competition or as a counterposition that's if not transgressive in nature, at least it shows a fundamental tension. I would say that I think I could speak for both Ross and I, and certainly many other modelers, in saying that statistical models and dynamic models are both essential tools in the toolbox of public health. Both are absolutely essential for informing our understanding of the world, but they're different, and they bring very different things to the table. And this is why, by counterposing them as two competing factions that are seeking to secure health science supremacy is really misguided. And it's equally misguided in the world of big data, which we are helping to contribute to. You will sometimes hear claims that we are entering the world, the post-theory world, that we need not engage in theorizing longer. What we will instead do is take lots and lots of data and append it to models and throw it at the wall and see what sticks. As a avid practitioner of big data and of data science, I think that notion is highly benighted, and you'll find lots of people who are less glamorously working with very informed-driven, very theory-driven, theory-informed models in the big data space, and who are proceeding very successfully using those models. Traditional statistical models do complement each other. Some of my colleagues prefer to refer to dynamic models as synthetic models and statistical models as analytic models. I haven't joined them in that appellation, but I think it's an interesting point about how they're different. One thing I will say is that, when we're dealing with empirical observations, which form the basis for statistical modeling, these observations of the world, they arise from these underlying processes. And there's some underlying causal structure to the processes that give rise to this data. A lot of people, when they first approach dynamic modeling, they get very caught up in I don't have data for this thing, so I can't do dynamic modeling, or I don't have data for this variable, so we can't put it into the model. That is fundamentally, you're missing big opportunities by doing that. And increasingly, my colleagues in statistical science, those who work with me, for example, in computational statistics, have rich latent variable models, which include many variables that are not directly measured, but are believed to be important from a theory-based perspective. So don't think that a true statistician leaves out variables where there's not data. Increasingly, with Bayesian approaches getting more and more prominent, there's a lot of models that do seek to include latent variables. So just be aware that when we're dealing with statistical models, we are dealing with associations that are observed between variables. And these associations are contingent. They are contingent on the underlying processes that give rise to this association. And often these processes will change when we intervene upon a system. So if we're thinking about trying to characterize, for example, the relationship of care-seeking frequency with certain types of morbid conditions, maybe it's certain comorbidities, maybe it's mental health difficulties, for patients who are presenting to a care facility, if we institute different discharge policies, different care processes, or we put in place better community options, we may find those associations change quite significantly. The types of findings that we secure from statistical models are therefore based on observations and contingent on observations that emerge from certain processes. The danger here, folks, is that if we try to count on statistical associations to guide us going forward in the context of a new intervention or in the context of significant demographic change or other changes within the external world, we will be doing something akin to trying to drive observing just out the rear view mirror. We're counting on things forward in terms of the associations in place being similar to what we've seen before. And if you're going around in a big track that's a very defined curvature, that may work okay. But if you're putting into place totally new interventions that are shaping new data-generating processes in new ways, what you see out the back window in terms of associations between different variables may be very different from what you see going forward. So we don't want to drive looking out the back window. We don't want to drive looking in the rear view mirror. We want to drive looking forward in a way that anticipates what's coming. And this is where dynamic modeling fits in. And this is what I found a lot of students get confused about, because they have statistical models where time is a independent variable and they can use it to try to look forward. They have projection models to try to project forward. What's the matter with that? Well, there's not a lot the matter with it as long as the processes that are generating these things stay fundamentally the same. But if we go into a counterfactual realm, that's when we start to need causally informed models that can ask what-if questions that are based on the mechanics of the system. If I change this, the system will change in these ways. And that's not going to be a typical statistical model, although there is some very promising work being done with causal statistical models that may be intersecting with this. So, here, within a dynamic model, we have a set of mechanisms that seek to allow us to ask robustly these what-if questions in a way that wouldn't be possible if you're contingent upon associations as they have been observed thus far. And we can, and I would note, some of the models Ross showed yesterday would be very rich vehicles for sort of observing associations within a model that you could summarize. And some of the models that are available from some of my work do the same thing. You could see very interesting associations, say, between income and number of presentations for care. And you will see, if you undertake an intervention, how different those associations may end up being. So capturing causal structure in dynamic models is something that typically goes well beyond what we do in classic statistical models. but allows us to, and it's motivated by the desire to reason more robustly about how system behavior will change in a counterfactual context. So I think that's all I have time to discuss on this issue of broad differences between dynamic and statistical models. But I will note in closing on this area that if we consider the sources of data associated with our models, we will find that that often there are many types of data used within our models which end up being derived statistically. Ross had alluded to this earlier, and I won't belabor the point, but certain types of analyses here that go into estimating of parameter values in many cases are based on statistical models. For example, in my group, we've done some quite extensive work with competing risks analysis to understand the ways in which certain features contribute to outcomes and then built in parameters from that competing risks analysis within a dynamic model. That was, in fact, much of its motivation. Alternatively, there may be certain types of regression analyses that seek to estimate beta coefficients or odds ratios associated with certain risk factors that might be aspects of heterogeneity within a dynamic model. And those beta coefficients may be used under the right conditions within the context of a dynamic model to serve as parameter values. So you shouldn't view, although dynamic models and statistical models are quite different in terms of what they're seeking to achieve, although you shouldn't view one as a substitute for the other, it is not true that they are merely solitudes unto themselves. In fact, statistical models will often inform directly the choice of parameter values, and indeed, maybe part of the underlying processes that are going on within a meta-analysis to yield those estimates that we then employ very fruitfully within our dynamic models, and in estimating the parameters which we incorporate more broadly within our models. By the same token, and this will be my last point here in this session, by the same token, the dynamic model can also very fruitfully serve to inform statistical models. Some of the nicest work that I've seen done, and it's been a type of work that we've employed quite considerably, uses dynamic models as data generating processes to produce synthetic data. Ross had alluded to this earlier. With the synthetic data maybe having noise added, having censoring going on, so certain data is not available, otherwise being sort of downsampled, maybe only available on an occasional basis, and using that to judge the efficacy of different statistical models for estimating characteristics of the underlying processes. So here we might be looking, for example, to derive an algorithm, a statistical method for administrative data to recognize diabetes based on physician diagnoses, based on prescription behavior of physicians, based on hospital lab test results. And we might simulate a population in our dynamic model, a bunch of agents who present for care, who get tested with appropriate sensitivities and specificities and error bars on those tests, and who undergo diagnostic procedures. And we might use that synthetic data to test how efficacious are different algorithms for estimating the number of diabetics. The key benefit, folks, in this case, the key benefit is with the dynamic model, we know the ground truth. We know the underlying situation with precision. We have someone who is known to be, in the dynamic model, a diabetic. And we see the degree to which the statistical model picks up the true status of that person in the model. So these synthetic empirical data experiments are quite essential to our work in machine learning, in applying techniques that seek to use diverse empirical data to classify things. But they're also an increasingly powerful opportunity for insight across the health sciences, for giving a really rigorous way to try to prospectively assess different statistical methods, which you might then deploy in a larger scale clinical trial. And you want to have the types of measures that are most reliable given the vagaries of the data reporting processes, the uncertainties involved in people's status between care-seeking appointments, et cetera. So just be aware that this interface between data and dynamic models is rich. Statistical models and dynamic models seek to do different things, but both complement each other in very rich ways. And I think the interface between them will evolve quite a bit in coming years. We're making stronger and stronger use of computational statistics and machine learning together with our models, such as that particle filtering I showed yesterday, to really complement models. And, you know, in the next 20 or 30 years, I'm expecting to see a lot of progress being made to figure out how these two techniques, each so rich, each so powerful, can best work together. So that's all I have comments for today. I think it's time for lunch. Ross, any announcements before we go?